3.8 times 10 to the 23rd. That massive number is the amount of kilowatts of solar radiation our sun pumps out every single second. Honestly, it's almost unfathomable. Now sure, just a tiny fraction of that actually hits Earth, about 1.8 times 10 to the 14th kilowatts. But to put that into perspective for you, the daily influx of solar energy onto the Earth is abundant enough to power our entire global population for 27 straight years. The energy is already there. We just need a better net to catch it.
Here is our roadmap for today's explainer. We're going to start with a macro-level look at the solar energy boom, then introduce the Perovskite promise. After that, we'll confront the massive stability catch holding things back, dive down into the quantum-level physics of tuning the band gap, and finally, we'll see how atomic engineers are building better solar cells. All right, Section 1, the solar energy boom and current tech limits.
We hear constantly about solar power replacing fossil fuels, but let's do a quick reality check. Despite that massive amount of free energy hitting the Earth every single day, solar energy only contributed about 4.5% to the worldwide electricity output in 2022. Yeah, it's up from 1.6% in 2019, so it's growing incredibly fast, but it is still just a tiny slice of the global energy pie. And a lot of that comes down to the limits of our current tech. You've got first-generation solar cells, mostly silicon wafers. You see these everywhere. They offer high efficiency, they're super stable, but they cost a lot to make, and they're completely rigid. Then you have the third generation. These are emerging technologies that are highly cost-effective, scalable, and capable of really novel, flexible applications. And sitting right at the very top of this third generation is the true star of our explainer.
Moving on to Section 2, the Perovskite promise, the holy grail of solar.
Researchers have essentially stumbled upon what many consider the holy grail of renewable energy, perovskite solar cells, or PSCs. They're cheap, they possess absolutely incredible optoelectronic properties, and compared to traditional silicon, making them is surprisingly easy. And this brilliantly illustrates the hype. The power conversion efficiency of perovskites has just skyrocketed. We're talking a massive leap from a measly 3.8% to an impressive 26.1% in just a few short years. And when you stack them in tandem with silicon, bam! They hit a staggering 33.9%. They are rapidly catching up to, and in some ways surpassing, literally decades of standard silicon research.
Which brings us to a pretty obvious question, right? If these things are so incredibly efficient, dirt cheap to make, and super easy to produce, well, why aren't they on our roofs yet? Why isn't every building an electric car coated in perovskite panels right now? Well, there's a catch, a fatal flaw that is currently keeping them out of widespread commercialization.
Which brings us to Section 3, the stability catch, environmental degradation.
So the villain of our story here is environmental degradation. Perovskite materials, as mind-blowing as they are in a pristine, climate-controlled lab, are incredibly delicate out in the real world. These cells are vulnerable to almost everything outside. They degrade super fast when exposed to moisture, oxygen, heat, and ironically enough, even the very light they're meant to absorb. They suffer from crystal defects and ion migration, which causes them to just lose performance over time. To make matters worse, standard perovskites fail to effectively capture the near-infrared spectrum of the sun. So they break down when you put them outside, and they don't even absorb all the available light. It's a double whammy. To fix this, scientists realized they had to zoom way, way in, right down to the quantum level.
Section 4, tuning the band gap, quantum-level physics.
Okay, bear with me, because this is absolutely crucial to unlocking the whole mystery. Every semiconducting material has what's called a band gap. You can think of it like a hurdle. It's the exact amount of energy a photon of light needs to bump an electron from its resting state, the valence band, up into the conduction band, where it becomes usable electricity. So the crucial point is this. If a photon hits the material with too little energy, it just phases right through, like the panel is entirely transparent. But if it has too much energy, it clears the hurdle, sure, but all that excess energy is violently lost as heat, which, as we just learned, degrades the cell.
Standard perovskite materials generally have a band gap of around 1.5 electron volts. That means they perfectly utilize the visible light spectrum, roughly 300 to 800 nanometers. But they are completely missing out on a massive portion of the sun's energy sitting over in the infrared region. If we want maximum efficiency out of these cells, we have to tune this band gap so it matches the sun's entire spectrum perfectly.
And that leads us to Section 5, building better solar cells through atomic engineering.
Now, what's really exciting about this is that scientists aren't just shrugging their shoulders and giving up. They are actually physically altering the molecular structure of these materials to solve the instability and the bandgap issues at the exact same time. Perovskites have a 3D cubic structure that basically acts like a highly specific set of microscopic Lego blocks. You've got an organic or inorganic cation right in the middle, that central A sphere, surrounded by a beautifully symmetrical cage of metal and halide ions. This specific geometric lattice is exactly what gives the material its magical solar properties and allows charge to transport so efficiently. But this structure has to be perfectly balanced.
To keep those microscopic Legos totally stable, scientists rely on something called the Goldschmidt tolerance factor. It's essentially a mathematical Goldilocks zone that needs to stay between 0.8 and 1.0. If the atoms you snap into this structure make the tolerance factor too big or too small, the entire 3D crystal structure literally collapses. It degrades into a non-photovoltaic phase, completely ruining the solar cell's efficiency and making it hyper-vulnerable to heat and moisture.
So how do they fix it? Enter compositional engineering. Going back to our Lego analogy, scientists can literally swap out individual atoms in that central A site. For example, by carefully substituting just a tiny fraction of the original atoms with a totally different element, like cesium, they change the physical size of the internal components. This pushes the tolerance factor right back into that Goldilocks zone. By doing this, they effectively tune the band gap to absorb way more of the sun's light, while simultaneously eliminating those fragile non-photovoltaic phases. The whole crystal structure locks tightly into place, and the material suddenly becomes highly resilient to heat and moisture.
Let's look at some actual numbers, because the concrete results speak for themselves here. A standard pure perovskite cell achieves about 14.2% efficiency. Not bad. But by swapping in exactly 15% cesium, scientists engineered a brand new molecular structure. That one tiny atomic tweak boosted the efficiency to 16.1% and perfectly stabilized the band gap at 1.52 electron volts. This is undeniable, real-world proof that tuning at the atomic level directly upgrades the power of the solar cell.
And when you bring all of these techniques together, the results are nothing short of extraordinary. Testing a heavily engineered quadruplication cell, which basically just means scientists meticulously mixed rubidium, cesium, and 2 different organic molecules to find the absolute perfect lattice structure, reveals incredible stability. Finding that exact sweet spot allowed it to hit a massive 21.6% efficiency. And here's the best part. After 500 grueling hours baking at 85 degrees Celsius under continuous light, it retained 95% of its initial performance. They literally conquered the stability catch.
Which leaves us with this final, provocative thought. We are no longer just crossing our fingers and hoping to find better materials out in nature. We are actively engineering them, atom by atom, to capture the sun's absolute full power. If we can dial in the perfect band gap, completely stabilize the crystal lattice, and make these cheap, flexible solar cells virtually indestructible, how quickly will our entire global energy infrastructure transform? The future of solar energy isn't just bright, it's practically here.